Let's first look at how threads should be represented by an operating system or a system library that provides multi-threading support, and also what is necessary for thread creation. Remember, during this lesson, we will base our discussion on the primitives that are described and used in Birrell's paper. These don't necessarily correspond to some interfaces that are available in real threading systems or programming languages. And in our next lesson, we will talk about pthreads, which is an example of a threading interface supported by most modern operating systems. So that will make the discussion a little bit more concrete. You can think of this lesson and the content of Birrell's paper as explaining this content at a more fundamental level. Well, first, we need some data structure to represent a thread, actually. The thread type proposed by Birrell is a data structure that contains all information that's specific to a thread and that can describe a thread. This includes the thread identifier that the threading system will use to identify a specific thread, register values, in particular the program counter and the stack pointer, the stack of a thread, and any other thread-specific data or attributes. These additional attributes, for instance, could be used by the thread management systems so that it can better decide how to schedule threads or how to debug errors with threads or other aspects of thread management. For thread creation, Birrell proposes a fork call with two parameters, a proc argument, and that is the procedure that the created thread will start executing, and then args, which are the arguments for this procedure. This fork should not be confused with the Unix system call fork that we previously discussed. The Unix system call creates a new process and as an exact copy of the calling process. And here, fork creates a new thread that will execute this procedure with these arguments. When a thread T0 calls a fork, a new thread T1 is created. That means that a new thread data structure of this type is created, and its fields are initialized such that its program counter will point to the first instruction of the procedure proc, and these arguments will be available on the stack of the thread. After the fork operation completes, the process as a whole has two threads, T0, the parent thread, and T1, and these can both execute concurrently. T0 will execute the next operation after the fork call, and T1 will start executing with the first instruction in proc and with the specified arguments. So what happens when T1 finishes? Let's say it computed some result as a result of proc, and now somehow it needs to return that result, or it may be just some status of the computation, like success or error. One programming practice would be to store the results of the computation in some well-defined location in the address space that's accessible to all the threads, and you have some mechanism to notify either the parent or some other thread that the result is now available. More generally, however, we need some mechanism to determine that a thread is done and, if necessary, to retrieve its result or at least to determine the status of the computation, the success or the error of its processing. For instance, we can have an application where the parent thread does nothing but create a bunch of child threads that process different portion of an input array. And the parent thread will still have to wait until all of its children finish the processing before it can exit so as not to force their early termination, for instance. To deal with this issue, Birrell proposes a mechanism he calls join. It has the following semantic. When the parent thread calls join with the thread ID of the child thread, it will be blocked until the child completes. Join will return to the parent the result of the child's computation. At that point, the child for real exits the system. Any allocated data structure state for the child, all of the resources that were allocated for its execution will be freed, and the child is at that point terminated. You should note that other than this mechanism where the parent is the one that's joining the child, in all other aspects, the parent and the child thread are completely equivalent. They can all access all resources that are available to the process as a whole, and share them. And this is true both with respect to the hardware resources, CPU, memory, or actual state within the process.